All right, welcome back everybody. We're going to do another video. Today's video is we're just going to work through the writ number 3. We handed that back to some people. We didn't get it back to everybody. There were a couple people missing class. It was at the end of class. Some people didn't get a chance to pick this up. So I wanted to work through this writ for you so you could look at this video and have this to study as you prepare for WPR number 1. All right, so let's just get to it and we'll work this problem. So we've seen this problem before, but the difference this time is we've got friction on this surface. So there's friction on this surface. So what's going on? Block 2 is suspended from a pulley. It's going down. It's pulling on block 1. It's pulling it up and to the right. We do have an angle here, theta, for our ramp. And the system, block 1 is accelerating in this direction. Block 2 is accelerating in this direction. And I will say this, that if you aren't assigned the direction of acceleration, that's important to know as we go through our process. We build our free body diagram. We point everything in that direction. It helps us determine if our forces are positive or negative. If we go through and solve for it in the end, and let's say a problem like this, we don't know if maybe block 1's significantly heavier and it would actually pull block 2 up. If you guess and you guess wrong, you'll figure that out because you'll just get a negative number. And that means that when you solve for it, it's accelerating this way with a negative number, which is direction, so it's actually going the other way. So it's okay that if we don't give you the acceleration, you can guess and then just be consistent with that the entire time. Oftentimes, though, we will typically give you the acceleration. So moving forward, we're going to assume that block 2 goes down, block 1 goes up. And we are solving for derive an algebraic expression for A. So this is our read step. Complete. Our task is to solve for A. Our task is to solve for A. And our physics step, never skip the physics step. Always do the physics step. Lots of points here. All right, this is a Newton's second law problem. So we've got Newton's second law is equal to, so the sum of the external forces, is equal to mass times acceleration. That's Newton's second law. And then we've also got friction here. This is going to be, it's moving. They gave us a kinetic coefficient of friction, so we've got our kinetic friction equation. It's our fun equation that the that the force of friction is equal to mu k times n. And I do want to point out really quick that even though force, this is a force, it's a vector, this is a force, it's a vector, we're not denoting the vector information here because it is not the direction that is the same, right? Friction will not point in the same direction as the normal force. Now the magnitude is going to be dependent upon the magnitude of the normal force, but they don't point in the same direction. So we don't put the arrows up here like we did for Newton's second law. We put the arrows here because that information for those quantities, the direction goes across the equal sign also. The forces will point in the same direction as the acceleration, or the net force will point in the same direction that the object accelerates. But down here, the friction force does not point in the same direction as the normal force, so we don't put vector signs on there. You could actually maybe be a little more specific and put the magnitude of the friction force is equal to this coefficient of friction multiplied by the magnitude of the normal force. But we can also denote that magnitude by just omitting the vector symbol. All right, good. So we'll move on. Read, task, physics, assumption. We'll go givens. So what is it that we're given in this problem? We can come back up and see we're given M1, we're given M2, we're given mu sub k, and we're given our angle theta. So M1, M2, our coefficient of kinetic friction, and the angle of the ramp. And then I'm going to include in here the acceleration due to gravity, g, because that's a given that this is happening near the surface of the Earth. All right, good. Moving on, draw step is complete. Draw step's complete. And then we've got our assumptions. So our assumptions are, we could say this, we could say that there's no air resistance on block 2. So no air resistance on block 2. It's in free fall. An important one is that our pulley is massless, right? Otherwise, you'd have to account for the pulley. We'll fix that later on. We'll add mass to the pulley. But for right now, the pulley is massless. We're also going to assume that we have an ideal string so that it's also massless. And that it doesn't stretch. The fact that it doesn't stretch means that block 1 and block 2 are going to move together. So those are all of our normal assumptions. So massless pulley and string. Massless pulley and string. Ideal string, meaning it doesn't stretch. And no drag, things like that. All right, good. All right, so let's move on from there, and we're ready to get into our solve step. Now, this is a Newton's second law problem with 2 objects. Each one of these objects are going to get their own free body diagram. So inside the solve step is where the first thing is where we draw our appropriate diagrams, and our diagram here is our free body diagram. So we're going to end up with 4 equations because we're going to do a free body diagram for mass 1. All right, we'll call this is number 1 is this is mass 1. This is mass 2. We're going to do free body diagrams for each of them, and then we're going to analyze that vector equation in both the x and y. So each mass will get 2 equations, total of 4 equations. We may or may not use all of them, but we're going to do that anyway. We'll always do that when we do our free body diagram. We always will analyze the x and y direction for that object by itself. So let's get started. Let's get over here. We're going to do mass 1. And over here, we're going to do mass 2. All right, we're going to draw our free body diagram for mass 1, which looks like this. All right, and so we've isolated the body. We're going to draw in all our forces, so we use want F for that. We'll just throw that acronym up here so we can reference it. So we've got a weight force for sure, pulling straight down, so that's mg, and this is m1, so it's m1 times g. All right, so there's our weight force. There is no applied force. There's nothing pushing on it. There is a normal force, though. Right, we've got a normal force going up like this. So there's our normal force, so no applied. There is a normal. There is a tension that's pulling it back this direction. So there's our tension force. It's there. And we have friction. So, and it's drawn back here at the bottom, and it's resisting the motion. And so we label that as our friction force. Check. And an important note, this is a common misconception where people will write here their coefficient of kinetic friction. This is the force. The force is the F sub k. Mu sub k is simply a coefficient. It's just a number. This is the force. So make sure you write that this is not the coefficient of friction, but it is the force of friction. So we've got 1, 2, 3, 4 forces, and they all happen to be different types. The only thing we didn't have was an applied force. All right, awesome. So that is our first step, and our second step in drawing our free body diagram. Now we have to pick a coordinate axis. We always point our axes in the direction of acceleration. We know that this object is accelerating up the ramp, right? It says that this system is accelerating in a clockwise motion. Let's see where it says. Coefficient of friction with respect to horizon, draw free body diagram, and of course, derive an algebraic expression. Okay, so it didn't say which way. It didn't say which way the object's accelerating, so we're free to pick a direction. So we picked this clockwise motion. All right, I guess I didn't do the Writ step thorough enough to begin with. That's fine. So we've got, we need to pick, we assigned acceleration up the ramp as being positive, so we're going to make that our positive x direction. So here's our y, here's our x, and this object is accelerating up the ramp. And if we get it wrong, when we plug in numbers, which we eventually do back on number 2, if we got it wrong, we'll get a negative number, so it's not a big deal. All right, so now we have isolated the body, we've drawn and labeled all of our applicable forces, we've picked our axes, and now that we've picked our axes, we can assign critical angles. And our critical angles go on any of our forces that are not pointing inside of one of the directions, exclusively in the direction of one of our axes. So anything that's off to the side. The only one is our weight force, right? Tension's completely in X, normal's completely in Y, friction's completely in X. But this weight force is it's going off to the side. It's in both the X and Y directions. So we've got to label our angle. So we go through the process of thinking about this angle, and if this angle gets smaller and smaller and smaller, as that happens, the surface here, this gets flatter and flatter and flatter. And our y-axes, if we overlaid our axes on top of this, so we'll come back to our weight force, that's the one breaking up, and draw our axes, all right? The x-axis gets flatter and flatter and flatter as that angle goes away. So this side gets a bigger angle. But the y-axis, you'll notice as this angle gets smaller, the y angle gets smaller and smaller and smaller. And when this angle goes to 0, that y-axis is straight up and down, and this angle has gone to 0. So we should feel confident in denoting that this is the same angle. This side here on the right, that's the same angle as the block, or as the plane, and we've done that several times in class, so we should be comfortable with where that angle goes in this example. All right, good. That completes our free body diagram for mass 1. While we're here, let's do it for mass 2. So we'll isolate that body. So here's mass 2. It's got a weight force, so we're going to go through the same acronym. Weight, pointing straight down on it. So there's M2G. There is no applied force. And a common misconception here is people just always, if there's a weight force, they want to put a normal force on it for some reason. But remember, when we use our acronym, only the weight force can be applied at a distance, meaning it can be there if nothing's touching it. Gravity, that's what Einstein's general theory of relativity was about, that gravity actually warps the space around an object. So we're not talking about that now, but what we are focused on is trying to identify the forces. Weight is the only one that we can have. Gravity is the only one right now in this class that we can have without something physically touching it. All the rest of these require something touching it. So once you assign gravity, ask yourself, what else is touching it? And for block 2, the only thing touching it is this rope. That's the only thing left touching it. That is going to give us a tension force. So the rest of those forces aren't there. I have no applied, I have no normal, I have no friction, I have a tension force. So, and that's from the top going up like this. All right, so there's our tension force. Awesome, and those are all of our forces. Now we do the third step in drawing our free body diagram for mass 2. We point our axes in the direction of acceleration. For this object, we've picked down as the direction of acceleration. So here is our x-axis, here is our y-axis, and we've basically just taken our axes and we've brought it over our pulley and rotated it down. So X is now still pointing in the direction that our system is moving, because for object 2, it's accelerating down. So we've got our x-axis down and our y-axis off to the side. All right, good. There are no angles, right? All of our forces acting on mass 2, just the tension and the weight force, those are both completely in the X. So there's no forces that are off to the side that we need to break up into components. So we have no angles that we need to indicate. So we're complete with our free body diagrams, and both of these have been done in accordance with the course supplement. Now we're ready to go on to our cut and paste step. And you do this for each of the forces. So M1 gets its own cut and paste step. Some of the external forces acting on mass 1. And I'm going to not put the 1 here because I'm going to try and drive home the fact this is a cut and paste set. So I'm just going to say equals mass times acceleration for now. And then I'm going to say that this is, then we write the next line, which is in the X direction and the Y direction. And this is now, we rewrite our Newton's second law, but in component form, because up here we had vectors, and down here we have the components, so mass times acceleration in X, and some of the forces in the Y equals mass times acceleration in the Y. And this is a cut and paste step, so I'm going to quite literally cut and paste it, which is what I've been trying to indicate in class, is it's the same for both. The only thing that we change, right? I just cut and pasted it over. Too bad you guys can't do that on your exam, right? The only thing that we change is we go in and we highlight that this is for mass 1. So I go back to each of these masses and I'm going to put in mass 1, mass 1, and mass 1. And I go over here to this mass and I'm going to put in the mass that I'm analyzing here, which is mass 2. So this is for mass 2, mass 2, and mass 2. So we've done our cut and paste step now for both, quite literally cutting and pasting it in when we did mass 2. Now before we go on and actually add up our forces, let's just take a second and we got to think about our acceleration. If we made the good life choice and pointed our axes, one of the directions for our axes, in the direction of the acceleration for our object, like we did here and here, in both cases it was the x. If we did that, we should be able to assign one of our accelerations as 0. And so our acceleration in the y direction is 0 because we did this by design. For both these objects, the acceleration in the y direction is 0 because we picked our axes to point in the direction that these objects are accelerating. So both of those are 0, and that will make our solving this problem significantly easier. All right, now we go back and we simply do what it says. So add up all the forces in the x direction and set that equal to mass 1 times the acceleration of this object. And because there is no acceleration in the y, the acceleration in the x is the acceleration of the object. That's all of the acceleration. So let's add up the forces in the x, and we're not doing this by memory or looking up here. The whole reason we did the free body diagram, we did this step. Some people want to, for some reason, compartmentalize these problems and come down here and they've forgotten that they did all this analysis. You did this analysis to let you write down the next line. So it says add up the forces in the x. Remind ourselves, this is the x direction. So what's pointing in the x direction? Well, I've got tension pointing in the x direction, and it's positive. I've got friction pointing in the negative x direction, right? It's negative. And then I've got part of the weight force, and it's going backwards, right? It's pulling this thing down, right? Here's kind of the delineation between what's positive and negative, and that is pulling us backwards. So that will also be negative. So I've got positive tension in the x direction. I've got the negative force of friction in the x direction, and I've got this negative component. Right? It's not all of the weight force, it's part of it, and we've got to figure out which part. So we do the same thing we've done before. We look at the angle, we see which axis is adjacent to it. It is adjacent to the y-axis, so y is going to get the cosine. We're looking in the x, so x gets the other part, which is the sine. So this is going to be t minus the friction force minus the x component of the weight force, which is mg sine theta. And we set that equal to m1 times the acceleration of the object. And I am just going to write a without the sub x because this is all of the acceleration of our object. All right, good. Now, we can go just a step farther on this line because this force of friction that we've put in here, we've got an equation for that. That's our fun equation. So let's go ahead and add that in as well. And now we know that tension minus our force of friction, which is our coefficient of kinetic friction multiplied by the really just the magnitude of that normal force for this object. And we've got, so multiplied by the normal force. We haven't done that yet to figure out what that is. Subtract the component of our weight force is equal to m1 times a. All right, good. And that's about as far as we can get with that. Now, let's look in the y direction. Remember, we're going to analyze all 4 of these directions. We may or may not use all of them, but we're always going to analyze them. So let's look at the y direction, add up all the forces in the y, and we remind ourselves y is perpendicular to the surface of the plane, so it's going this direction. We've got the normal force that's completely in that direction. It's pointing up, so it's positive. And we've got the weight force going down, so we've got that component of the weight force that's going to be negative, that y component. And we already found that that's going to be the sine piece, or excuse me, the cosine piece. So the normal force going up minus the weight force going down, and set that equal to 0. All right, and what we normally find in the y direction when we're doing these pulley problems is we're finding the normal force. That's what this is going to give us, is what the normal force is. So the normal force, if we solve this one more step out, is equal to m1g cosine theta. All right. We could do a quick inventory. We could have done it after this first problem of what it was we were solving for, A, and what we were given, and see how close we are. Because here's the thing we want. And in theory, I could divide by m1, and I have an expression for what A is. And it's a true expression. The problem is it's not in terms of the given quantities. I have a t over here, not a given, right? I cannot write my expression in terms of t because you don't know it. I've got mu sub k, that coefficient of kinetic friction. That's all right. It can stay. I've got this normal force, though, and that's not a given. I did not give you what the normal force was, so you have to get rid of that n. So we got to get rid of t. We got to get rid of n. Everything else is given. m1's given, g's given, theta's given, m1 again was given. So it's just this t and this n that I've got to get rid of. T has got to go away, so I'm going to have to find an equation to get rid of it. N's got to go away, so I've got to find an equation to get rid of it. And we've already found the n, right? Here's the n, the normal force. So we can take this and plug this in for that normal force. And so that'll allow us to get rid of the n. And that's fine because our expression for n is in terms of m1, g, and theta, all of which are given m1, g, and theta. So we're going to eliminate that normal force with a little bit of algebra. And when we do that, we get now that tension minus our coefficient of kinetic friction multiplied by that normal force, which is now m1 times g times the cosine of the angle, minus m1g sine of the angle equals m1a. All right, awesome. Now, that's pretty much as far as we can get analyzing block 1, and we still have to get rid of this tension force. And we have no other equations here because it doesn't live in the y direction. I've got to get rid of it. But fortunately, that tension force does live over here with m2. So if I analyze m2, I'm going to get an equation with tension, and maybe we'll be able to get rid of it doing some algebra. So let's go over here to block 2. And let's analyze it. So we're going to do exactly what this equation says in the x direction. We're going to add up all the forces pointing in the x direction, set them equal to m2 times the acceleration of the x. And if we remind ourselves, x is pointing down. Positive x is pointing down. I've got one force in the positive x direction. That's m2g. So it's positive, right? And as a reminder, g is always a positive quantity. We take care of the direction for the acceleration due to gravity when we put in the direction for this force. So this one was negative, and we put the negative there. So when you plug in this number, it's always a positive 9.807 meters per second squared. You took care of the negative sign right there. And this one doesn't get the negative sign right there. This is a positive because we've identified it as down as being positive. So don't plug in negative 9.807. Get that out of your head. G is always a positive number. You take care of the direction of G when you do your analysis beforehand. So we've got the weight force down, which is positive, minus the tension force, which is pulling up, right? Tension's pulling up, which is the opposite of the positive x direction, so it gets the negative, and that's going to be equal to m2 times the acceleration of this object, which, since this is an ideal string, right, we said this is an ideal string that's not stretching, m1 and m2, they're going to accelerate together, so the magnitudes, not the direction, but the magnitude of those accelerations will be the same, and here I'm dealing with the magnitude, so this A and this A are the same thing, they're both the thing I'm trying to solve for. All right, and that is a complete expression. We can go over to the y direction, and if we look and analyze, there are no forces acting in the y direction. This is like the one time that there's zeros on just both the left and the right hand side, so we can come back and say there's no forces, there's no acceleration, nothing's happening. So we've analyzed this one and found that there's nothing there to look at. So we've now done all 4 equations. This one on the right just gives us 0 equals 0, which is a good comforting thing, hopefully, for us and allows us to sleep better at night. But here we'll notice we've got an equation with t in it, which is what we were hoping to find. Our equation on the left, we've got t, which we don't know, and a, which we don't know. A is what we're going after. So one equation with 2 unknowns. Here we've got, again, m2's known, g's known, m2's known, t unknown, a unknown, but the thing we're going after. So we've got a system of 2 equations with 2 unknowns, t and a, t and a. This problem could have, instead of asking you to solve for the acceleration, we could have asked you to solve for t. Maybe we went back here and said, find t, instead of finding a. You would have done everything to this point the exact same if you were solving for t. The free body diagram's the same, analyzing the forces is the same, these equations, nothing would be different. The only difference would be now which of these 2 unknowns you want. We, in this problem, are asked to find the acceleration, so we're going to go after a. But if you had done this and you were told to go after t, you would simply get to the exact same point, and instead of eliminating t to find a, you would eliminate a to find t. So that would be the only difference. None of the analysis, none of the work is different. It's the exact same physics. So what I've noticed for some reason is a lot of people will naturally look at this equation and say, I want a, so I'm going to solve this for a. It's actually the opposite of what you're doing. If you have a system of 2 equations and 2 unknowns, you solve for the thing you want to get rid of, not the thing you want. So we're going to solve this equation for the thing we want to get rid of, which is t. I want to get rid of t, so we're going to solve this equation for t by multiplying t to the, or add t to the other side, and then subtract. So we're going to add t to the other side, we're going to subtract m2a, and we're going to get this expression m2g minus m2a is equal to t. All right, this is an expression for what t is. We can now plug that expression for t into our other expression, and we will have eliminated t, and you get m2g minus m2a minus mu k m1g cosine theta minus m1g sine theta is equal to m1a. Now I'm solving for a, and it exists in 2 spots. I can't just divide by m1 and say here's a. It'd be a true expression, but it has not solved for a because I have to get a on the same side. So we're going to add m2a to both sides. And when we do that, we get this expression that m2g minus mu k m1g cosine theta minus m1g sine theta equals m1a plus m2a. And we can look at this as there's been the distributive property. The a's been distributed throughout, so we're going to undo that distributive property and rewrite this as m1 plus m2 times a, right? Where the a had been distributed and been multiplied by each. So this is the same thing. And now we can divide by the m1 plus m2, and we get, and I'm going to write it down here because we would need this for our second problem, but a is equal to m2g minus mu sub k times m1g cosine theta minus m1g sine theta, all divided by m1 plus m2. All right. And I do like to point out in this expression right here that this is Newton's second law, right? There are three forces that are external to this system. Tension's not external. The three forces external to the entire system is I've got gravity pulling down on this object, I've got gravity pulling down on this object, and then I've got the friction pulling back on this object. Well, the one that's positive, that's accelerating the system, is the weight force on object 2 pulling down. That's the one accelerating it. The weight force on block 1 is slowing it down, and friction is slowing it down. So if we look at this equation, there's the weight force on block 2. That's a force, and it's positive because it's speeding it up. Here is the friction force on block 1, and it's negative because it's slowing it down. Here is the weight component, right, the piece of the weight force on block 1, and again, it's negative because it's slowing it down. And when you add up all those forces, right, you add up the external forces, that's equal to the mass. Well, I've got m1 and m2. That's the mass multiplied by the acceleration. So there's information when you leave this in terms of the variables that you should be able to identify. And then we should also be comfortable that when I add these all up, this is in terms of force, then divided by mass, which will always give me units of acceleration, specifically meters per second squared. So this is we are comfortable with this answer. We've analyzed the units. We did a little thought process about what the letters all mean, and we're pretty good with this answer. So we are complete with number 1. That is the correct answer. Now with number 2, I'm not going to work through the numbers. I'm not going to work through the numbers on what this is. But what I am going to do is basically talk about what's going on and how you do it. So it says that this object starts from rest. So number 2, we're looking back, assuming the block 1 in problem 1 started from rest. So we're doing this problem, and we're saying, assuming block 1 starts from rest, how fast will it be going, right? How fast? And that's asking about speed. So what is its speed or its velocity after 1.47 seconds? All right. This is a kinematics problem. So if we were to have done the read step and then the task step, we're trying to find the magnitude of the velocity, how fast it's going, its speed. And we do our physics step. This is now a kinematics problem. It's a 1D kinematics problem. And we could write all 3 of our equations down, but the only one we're going to need is that our final velocity is equal to our initial velocity plus our acceleration times time. That's the kinematic that we're going to use. We get our acceleration from problem 1. We just take, because here we need m2, so there's m2, plug it in. We need m1, so plug in m1. We need mu k, so there's our coefficient of friction. We need theta. So you just plug in all these numbers. You solve for an acceleration. Let me see if I've got that right here on me. And I can tell you what the number should have been. So you can work this problem if you want to. I think I've got that here somewhere. Give me just a second. So let's see here. I thought I had a copy of that with me. Yeah, so I think you get somewhere around 5.6. So your acceleration should be around 5.6 meters per second squared. I think it's 5.61 meters per second squared. It should be 3 sig figs. And then when you plug that into this equation, your kinematics, your initial velocity is 0, right? So our initial velocity is going to be 0. And so we simply get that our final velocity for our block is going to be equal to our acceleration multiplied by time. So you multiply this 5.61 meters per second squared times the time of 1.47 seconds. And I think you should get that the final velocity is right around 8.25 meters per second. And that should be your answer. All right, so we'll move on from there. And let's look at problem 3. I'll try and do a little better job on the read step this time and make sure we're good. All right, so a terminal velocity of a cat falling in air depends upon the weight and the area of the cat facing the fluid, which is just the air. Calculate the terminal velocity in meters per second and kilometers per hour. Ooh, let's underline that so we don't forget. And kilometers per hour. Of a 6.15 kilogram cat, I hate using numbers, falling in a pike head first position with a surface area. So the area is 0.505 meters per second squared, assuming that the coefficient of drag is 0.618 and the density of air is 1.21 kilograms per meter cubed. Okay, all right, so this is a terminal velocity problem. It's a drag problem, and we're going to have to execute this as such. So here we go. So let's go after what is it. Let's use our problem-solving process to get after this. So we've done the read step. The task is to find calculate the terminal velocity. So right here, that is our task. So we are looking for the magnitude of that terminal velocity. So we'll put in absolute value symbols to indicate we're looking for the magnitude, but it's the terminal velocity we're looking for. How fast this cat falls in when it's just in a free fall, which is okay because I'm a dog person. So moving on, read task physics. Never skip the physics step. This is going to bite some people on WPR1. They will skip the physics step, try and jump into the solve step. They will forget one of the equations or a couple of equations that they are supposed to be using. And if you don't get the answer right and you did not do the physics step, I cannot give you credit for those equations. So you have to do the physics step. Write down the equations you need. And if you don't remember, if you can't think of all of them at the beginning, write down the ones you can remember. And then as you work the problem out, if you come across another one, go back and add it to the physics step. Well, we've got drag in here. So we obviously need the drag equation. So our drag equation says that the force of drag is equal to 1/2 this c, which is our coefficient of drag, multiplied by the density of the fluid it's falling through, so the density of air, times the cross-sectional area of the object multiplied by its velocity squared. So that's our drag equation. It's on your PRC. And we're also going to need Newton's second law, because this is a Newton's second law problem. We've got forces, we've got masses, right? We gave you the mass of the cat. We don't use masses in kinematics. So if I'm giving you forces and I'm giving you masses, we're dealing with a Newton's second law problem. So sum of the external forces are equal to mass times acceleration, just like that. That's what we're doing. All right. We can go through our givens. So what are we given? I'm not going to write down the actual numbers, but we're given the mass, which is m1, or just the mass, the m for the cat. We're given c. We're given our density of air, which is rho, and we're given the cross-sectional area of our cat A. So those are all the things we're given, and we're also going to be given this is happening near the surface of the Earth, so its acceleration, the force of gravity is going to be caused by the force of gravity, and that'll be the acceleration due to gravity near the surface of the Earth, which is g. All right, good. So those are all our givens, assumptions. All right, our assumption is going to be that it's falling at terminal velocity, which if it's falling at terminal velocity, means that the velocity is now a constant, right? At terminal velocity, that is the point. So let's talk about terminal velocity for a second. If I drop something and start it from rest and do its free body diagram, it's got a weight force, and I'm going to draw it really big. So this is its weight force, and it causes the object to move down. And so it starts to move down. Originally, it has no velocity here, but it starts to move down. Now, as it's moving down, it's encountering air, right? There's all this air around here that wraps around this object and starts to slow it down. Think of your arm out of the car as you're driving, right? If you just stick your arm out and there's no wind and your car's not moving, there's no air resistance pushing against your arm. But as you start to accelerate your car and go faster and faster and faster, the wind pushing against your arm starts to, get stronger and stronger and stronger. So as this object starts falling, there's a small force that then becomes bigger and bigger as the object speeds up. So this drag force gets bigger and bigger and bigger. And eventually it becomes, and I'm going to have to move it down to do this, eventually it becomes the same size, and our magnitude of vectors are denoted by the length that we draw them, but it becomes, this should be drawn the same size, I'm not sure if it's exact, but our force of drag will be the exact same size as our weight force. Those lines are the same, and when that happens, our forces acting on the object, when we go to do Newton's second law and add them up, I'm going to have the same number pointing up that I've got pointing down, and those add to 0, which means the acceleration will be 0. That's what's happening at terminal velocity. You can't get any faster because your acceleration is now 0 because the forces are in balance. Terminal velocity is a state of equilibrium. There's still motion, but it's at equilibrium because this object, its motion's not changing in that it's not accelerating. The forces are balanced, acting on it. They're the same size. So acceleration 0, and however fast you're moving, you stay moving at that speed. You don't get any faster. That's why we call it terminal velocity, because it's the resultant velocity once this condition is met. All right, so now we're going to do the solve step, and I've already kind of started the free body diagram over here, so we're just going to grab that and use it. Well, let's not. We'll grab all this, move it down. We'll come back to our solve step because we've not done our draw step, and I want to drive home that the free body diagram is not in the draw step. So let's do the draw step where we've got this cat, and I am not going to make any promises. He's falling in a head down position, so he's kind of like this. There's his head, and we've got some legs. Ooh, this is a beautiful cat. Beautiful cat. There's some more legs. All right, here we go, and here's his tail. All right, there's our cat falling in a head down. He's moving this way. I don't know why his face kind of looks like a dinosaur. All right, he's not very happy. And we've got air resistance that he's encountering that's slowing him down. So there we've done our draw step. His velocity is down. And we've got drag, the air resistance that's slowing him down. All right, so now we'll do our solve step, and our solve step is started with our free body diagram. We've already isolated our object. An object in free fall is a pretty simple free body diagram, right? We've got the weight force, which is our only force at a distance where there's nothing touching it. There is something touching it to cause this drag force, right? This air is touching the object, so we're not going to assume away. In the past, we've assumed no air resistance. You can't do that and do a drag problem. There is air resistance. That's the thing touching it. So we've got a drag force that is caused by, it's being caused by the air that the cat is touching. And so that's slowing it down. Those are our only forces. Next, we do our axes. Now, we're just going to keep our same axes we've already done, which is just our normal X and Y like this. If you remember, we always point our axes in the direction of acceleration. So typically we point X, so maybe we'll rotate this, in fact. So we'll take this and we'll rotate it, because this might be what some people want to do, and we'll have X down and Y to the side. I don't know. It doesn't matter this time, and the reason is because this object, the forces balance in both directions, so our acceleration is going to be 0. I can pick any direction I want. Now, it does make sense to have one of the directions pointing in the direction of the forces, which are up and down. Otherwise, I'd have to break these apart. And let's not make it harder than we need to. So we either need X pointing that way or Y pointing that way. We'll make x point that way just because we want to stay consistent with x pointing in one of the directions we're working with. And now we're going to do the cut and paste step. I'm going to drive home the fact even more that this is a cut and paste step. So I'm going to come back up here where we did this before, and I'm going to grab our cut and paste step from a previous problem. I'm going to grab that and copy. And we're going to come down here and we're going to paste that in. And this was M1. We called this M1. So M1's the same. It's exactly the same. The only difference we've got now is before there was no acceleration in the y direction, which is still true, but now there's no acceleration in the x direction either. Both of our accelerations are 0 for an object falling at terminal velocity. That's the big takeaway. That's the big ticket. So, all right. Now that we've done that, we're ready to do what the problem says, which is add up all the forces in the x direction, set that equal to 0. All right. Well, we've got two forces. We've got the weight force going down and the drag force going up. So let's add those up. We've identified down as positive x. So m1g is positive minus the drag force, and that is equal to 0. And in the y direction, we still look there to make sure we're not missing anything, but there are no forces in the y direction. So this equation simply gives us that 0 equals 0, which is a true statement, and hopefully we can sleep better at night. All right, let's come back up over here now. We're going to work with this a little bit more. So we've got, we'll just copy it up here. So put it right there. Oh, I didn't need this part. So we've got the weight force minus the drag force equals 0. So we can add the drag force to both sides, and we get m1g is going to be equal to our drag force, but we know what our drag force is. We've got an equation for it right here, and we got that off of our PRC, and you have the PRC because we love you here in the House of Pain. And so you get 1/2 c times the density of error times the cross-sectional area times the velocity squared. Now, some people might think, oh, I can just skip to this, because in terminal velocity, you're going to get to this equation that the weight force is equal to the drag force. However, if you get the answer wrong, this is all kinds of opportunity for partial credit that you are denying the instructors the opportunity to give you. And I've quite often seen people get the wrong answer and they've written very little on the paper. So the only thing the problem-solving process can do, the only thing this problem-solving process can do is help you. And if you decide not to use it, that's your choice. I hope you get the right answer still, but if you don't, you're denying us the opportunity to give you partial credit. And I would not do that if I was you. But you are free to make your own choices. So now that we've got our equation of motion, this is a good time to go back. We've got our equation of motion. Let's go back. What is it we're solving for? We're solving for velocity. You always want to do that before you start your algebra. Double check that what it is you're solving for and your givens, and make sure that your expression is in terms of the thing you want, which is velocity, and your givens, which we are good because we got M1, G, C, rho, and A. So all of those are givens. This is simple algebra at this point. We're just solving for V. So we multiply the 2 up. We're going to take our 2. We're going to multiply it up. We're going to divide by C, divide by rho, divide by A. And we're going to get 2 times M1G divided by C rho A is equal to V squared. And then we take a square root of both sides, and boom, square root of both sides, and we get an expression for velocity. So velocity is equal to 2 times m1 times g divided by our drag coefficient, our density of air, and our cross-sectional area. So if you do that correctly and you plug in your numbers, the number you should get for this will be 56, I believe it's 56.5 meters per second. That should be your answer, but make sure you remember, and we did this just so you could practice paying attention to the read step. We asked for both in meters per second and kilometers per hour, so you need to convert this also. So there's one answer, but this would not be full credit. You also need to convert it to kilometers per hour, and if you do that correctly, you'll get 203 kilometers per hour. All right, so we need both of those to get full credit for this problem. All right, awesome. And now we're down to our last problem. And this is the one we worked out in class. I'll work it again. It's a good opportunity to do some more free body diagrams and practice some Newton's second law problems. So read step. 2 blocks connected by a string are pulled at a constant velocity. Ooh, constant velocity, that's important. Equilibrium, again, that simply means constant velocity. We're going to have actually the same type of thing going on as we do in this drag, in that we're going to have, it's not a terminal velocity, but we're going to have a constant velocity. So our accelerations, both directions for all objects, are going to be 0, right? Because it's a constant velocity, there is no acceleration. Across a horizontal surface by a force, this force F, applied to one of the blocks as shown below. The coefficient of kinetic friction between the blocks and the surface for both is 0.17. And then we're given inside the diagram here the angle 60 degrees, mass 1 is 1 kilogram, mass 2 is 3 kilograms. So I'm going to relabel these because you know me, I don't like numbers. We're going to deal with M1, M2, and theta. We're going to deal with F, that's already denoted, and then we've got our coefficient of friction here, mu sub k, which is between both blocks and the surface. It's got the same coefficient of friction. All right, so we've done our read step. This is our draw step over here, so that's complete. We'll denote that right now. Our task is to find F. So we're looking for the magnitude of F. So how big is this thing? So the magnitude of F. Physics step. Remember, never skip the physics step. Hopefully I've said that enough by now. Never skip the physics step. Newton's second law problem. So we're going to have the sum of the forces, sum of the external forces is equal to mass times acceleration. We pull this directly from our PRC. And we've also got friction here. So we're going to have our equation of friction, which is the force of friction equals mu k times n, with no vector signs on that equation. And we've already discussed that. All right, next, assumptions. Our assumptions are that this is moving at a constant velocity, which means the acceleration, actually let's do it this way, the acceleration of this object is equal to 0, right? Because acceleration is a change in velocity, and if the velocity is not changing, then the acceleration is 0. So acceleration equals 0, and our givens, we'll do this over here by our draw step. So our givens are going to be M1, M2, theta, mu sub k, and g. Right? So our answer needs to be in terms of these quantities and nothing else. And that's the thing we're going after. We'll come back to that after we come up with our equation of motion, just to make sure we know that our expression is an acceptable answer. You can't turn an answer in terms of stuff you don't know. All right, so moving on. We're ready to do our solve step. And our solve step always starts with the appropriate diagrams. In this case, we're going to do free body diagrams. We've got 2 objects that are accelerating, so we're going to do 2 free body diagrams. So you've got, we'll do this for M1, and we're going to do this for M2, and we'll do free body diagrams. None of them are on a plane or some kind of an angle, so all of our free body diagrams are going to be, well, this thing's supposed to work better than that. I'm going to keep going until it works. There we go. All of our free body diagrams are just going to be flat like this. And we've got a small one, and we've also got a bigger one for M2. So there's the bigger one, and this is our smaller one. There we go. All right, and so we've isolated the body. we're going to work through our acronym WANT-F and make sure we identify all the forces acting on this object. So we'll do block 1 first, and we've got a weight force acting on it. There's our one force at a distance, and now we just need to think through what's touching it in order to figure out all the other forces. So weight's good. An applied force, do I have anything pushing on it? Nothing pushing it. So there is no applied force. Normal force, it is resting on a surface, so there is a normal force going up. Yeah, this thing doesn't want to play now. There we go. A normal force going up. There is a rope pulling on it, so I've got a tension force to the side like this. So there's a tension force, and there is friction mentioned, so I've got friction dragging backwards like this. And as stated before, this is always denoted with the force of friction, not the coefficient, right? This is the force of friction, not the coefficient of friction that goes in our free body diagram. And now we make our axes, and again, this is just like the drag problem where it really didn't matter where we put our axes. The important thing is that you want to have your axes. If there is no acceleration, then look at the direction on your forces, and if I was to come up with some crazy rotation for my axes like this, then I'd have to break up every single one of these forces. That would just be a terrible life choice, so let's not do that. And we can just use the same axes that we've been using, unrotated x and y, so x to the right, y is up. And it doesn't matter this time because nothing is accelerating. So our number one rule, you got to point the axes in the direction of acceleration. But if nothing's accelerating, then make a good life choice and point it to where your axes are in line with as many of the vectors as possible. And so there, we've got it in line with it. All right, so, and there's no angles for anything as denoted, so we are complete with that free body diagram. So let's jump over to M2. M2, and we did finish, there was a normal force, there was a tension, and there was friction, so we had 4 of the 5. In M2, we're going to work again through WANT-F, and we've got a weight force going down, that is M2G. We've got a normal force going up, that is our normal force there. And we're going to denote these as different normal forces. So I'm going to make this N2. And I'm going to come back over here to M1 and call this N1 because they're different normal forces, right? N1 is acting on block 1, N2 is acting on block 2. They're going to have different magnitude. We don't want to get confused. So we'll denote it that way. This is also going to have, so I had the weight force. There was no applied. We've got the normal force. There's a tension pulling back this way. So there's our tension force, and there is a friction force also pulling back this way. So there's our friction force, and these are different friction forces again. They happen to be the same magnitude tension forces, but the friction forces are different. And then we've also got this. This would be an applied force, right? There is an applied force. Or really, this would be another tension force because it's pulling on it. I'm just going to label it as F, this other force here that's acting on it. You could say it's an applied force, but it's not really pushing on it. It is pulling on it, so it really would be more of a second tension force. There's probably a rope there pulling on it, but we'll just label it as F because that's the thing we're going after. And that way we keep F in all of our equations so we can quickly identify the thing it is we're looking for. All right, now we got to, again, label an axis. And most of nothing's accelerating, so we're not tied to an axis in a specific direction. But let's just keep the same axes that we picked for the other one. This is a good intuitive axis. And you'll notice that most of our forces, the normal, the tension, the force of friction, and our weight force are all going to be in either the x or y direction. The only one we have to worry about with any angle is this force. And we have to draw that with respect to our axes. So if we overlay at the beginning of this our axes, we know now that we want to either draw the angle here or here, and it happens to already be drawn for us there, so this is a super easy angle to find. It's right there, and it's adjacent to the x-axis. And we'll need that when we break that force up into its components later on in our Newton's second law analysis. So now we're ready to do the cut and paste step on our analysis, and I'm hopefully driving this point home. I'm going to come up here and I'm going to grab the cut and paste step from another spot. And this may or may not work as well as I'd like it to because I've got other stuff on it. So we'll see if I can delete these things off, and we'll do that analysis separate. Well, that didn't work. Well, I think you get the point that this is the simply copied, so sum of the force in the y equals m1. Oh, no. There we go. So that's what we were trying to cut and paste, and we'll cut and paste it for m1. We'll grab it again and do it for m2. So there's our cut and paste step. And the only difference for m2 is these m1s are now all 2s. So we're going to turn all those 1s into 2s because we're looking at m2 on the right. All right, perfect. So we've now split this up. We are going to analyze m1 in both the x and y. We're going to analyze m2 in both the x and y direction. And we'll come up with our equations of motions there. And there's a lot of stuff going on here in both x and y. So this is a good opportunity to add up all these forces together. But we do need to take a second and identify what is the acceleration for both. So remember, our assumption that constant velocity means acceleration is 0. So this becomes 0 in the x direction and 0 in the y direction. For both objects, all of these accelerations are zeros. This is like my favorite problem because so many zeros, all the zeros. All right, and now we simply do what the problem says. Add up all the forces in the x direction and set that equal to 0. Add up all the forces in the y, set it equal to 0. And then for block 2, same. Add the forces in the x equal to 0, add the force in the y equal to 0. Everything needs to balance out. All right, so if we add the forces in the x direction, we come back here to block 1, remind ourselves what's the x direction, what's pointing in the x. I've got tension, I've got friction. Those two forces, one's positive, tension's positive, friction's negative because it's pointing backwards. All right, and those have to add up to 0. All right, we can move on to the next one. Add up all the forces in the y. I've got this normal force in the y. I've got weight force in the y. The normal is positive, so N1 minus M1G has to equal 0. And we continue doing this now for block 2. For block 2, in the x direction, I'm going to have a component of this force, and I've got two forces pulling backwards. So I'm going to get the x component of F minus tension minus friction equals 0. And in the y direction, I've got weight, which is negative, and the normal, which is positive. And I've also got a y component of this force. It's pulling in the y direction as well. So I'm going to get N2, which is positive, plus the y component of that force I'm going for, minus gravity, the weight force, excuse me, minus the weight force, which is mass times the acceleration due to gravity, is equal to 0. All right, those are our 4 equations. We can do a little more though. We know we've got these forces of friction. We know what those we've got an equation for what friction force is, so we're going to substitute that in. And we can, move the negatives to the other side to make these expressions a little bit more simple. So we'll just move all the negatives to the other side. And then we can also break apart these components on the force that we're solving for. So this is the x component, and here's the y component on that force. Well, we can come back up here and say, well, we know that the adjacent side is the x, so the x is going to get the cosine for F, and the y is going to get the sine. So we're going to put in all those different pieces right now, and we'll start over here for M1, we'll start over here on the x direction, and so we're going to get T is equal to the friction force, which is, using our equation, mu k times its normal, which is N1. All right. What is it we're going after again? We're going after F. Well, there's no F here, right? There's actually no F in this side at all. You probably would have started in 2 going after F, but you'll see you need what's in for block 1 anyway. And now we'll simplify the y direction. We get n1 equals m1g. That's as simple as we can go there. For the x direction for block 2, we get the x component, which is f cosine theta, minus the tension, minus the, or excuse me, we're adding those to the other side. So f cosine theta is going to equal the tension plus the force of friction, which is mu k times its normal force, so an N2. And then in the y direction, we get N2 plus the y component of our force we're going for, which is sine theta, is the y component, and that has to add up, that has to equal m2g. All right, those were all those simplifications we talked about. And now let's see where the force is. Let's do a quick inventory again of what we want and where it's what we can use. So we're going after f, and we can do it in terms of these variables. So here's f, which is in terms of some of those variables, but it's got this normal force, not given, and it's got this tension, again, not given. So here I've got another equation with that normal force and the force I'm going for, and everything else is given. So here's one equation with 2 unknowns. This equation has 3 unknowns with a tension. There's the equation with a tension, but it introduces another unknown. And then here's an equation for that force. So really the only one you can solve for right now and just plug in givens is this normal force, which you can then turn and plug into here and solve for the tension, which you can then plug into here and you'll get the tension, but you still have this normal force here, so you'll need to solve for it, plug in, and then solve for the final. So we have 4 equations and 4 unknowns. N2, tension, F, and N1. 4 equations, 4 unknowns. That's a lot of algebra, but we can survive. We'll make it through. So we'll start by plugging in N1 into T, and we into the x direction, excuse me, and we get that the tension is equal to mu sub k times m1g. We've eliminated one of our variables that we need to. So now we've solved this equation for another thing we don't want. That's the key, is always solve these equations for the thing you want to get rid of and then plug it in. So we want to get rid of t. We've already solved for t, so let's plug that in here, and we've now eliminated t. So if this gets plugged in there, we get f cosine theta equals t, which is now mu sub k times m1g, and don't forget your m1s versus m2s, plus mu sub k times n2. And now we've got this equation, but we need to get rid of n2. So if we solve this equation for n2, we get n2 equals m2g minus f sine theta, and we can take that and now plug that in for n2 to eliminate n2, and we get f cosine theta equals mu sub k m1g plus mu sub k times n2. Well, n2 is m2g minus f sine theta. And this is a true statement. This is the fundamental equation of motion, and it is in terms of everything that is given. We were given theta, mu k, m1, m2, and g, and the thing we're going for, which is f. So now we just have to solve this for f. Unfortunately, it's in 2 spots. We've got it over here on the left-hand side, and we've got it 1 spot on the right. So we're going to have to, we can't just divide by cosine theta. It'd be nice if we could, but that would have f inside the solution for f. That's like using the definition of something in a sentence, or using the word you're trying to define in the sentence. You can't do that. So we need to get f all the way over to the left-hand side. So we'll start by multiplying this mu k out using the distributive property, and then we get f cosine theta equals mu sub k times m1g plus mu sub k times m2g minus mu sub k times f times the sine of theta. And now I can add that. I can add this term to the other side, and I've got all my f's on the same side. So I get f cosine theta plus mu sub k times f sine of theta is equal to the terms that are left. And I'm going to simplify these terms. I've got both of them have a mu k, both of them have a g. So I'm going to go just make that mu k times g multiplied by m1 plus m2. And you'll notice this is the same thing. If you distribute the mu kg through, I get mu kg times m1, mu kg times m1, and mu kg times m2, which is this one, mu k m2g. All right, so that's the same thing. And over here, a lot of distributive property. Here we're going to undo the distributive property. We're going to pull this f out also and make this f times cosine theta plus mu k sine theta. And that's equal to the right-hand side, which we're not changing. All right. And now I simply divide the left-hand side by this term inside the parentheses, and I get a final expression for what f is. And our final answer is that f is equal to mu k times g times m1 plus m2 all over the cosine of theta plus mu k times the sine of theta, like that. And that is, in fact, our answer. Perfect. And we were given numbers. We were, in fact, given numbers. So if you plugged in all these numbers and worked through the problem, this one, you have to be careful. So you have to be careful. This is in two significant figures. So your solution here needs to be in terms of two significant figures. And when you actually work that out, you get an answer when rounded to 10. We indicate 10 as two significant figures by putting the decimal point. So plugging in the numbers, we'll get 10 newtons is our the answer for what that force is. So it's 10 newtons. All right, and that concludes all of our video for how to do Writ number 3. And just a reminder, we had problem number 1. We had a simple Newton's second law problem with friction involved, and we had two masses. So we did a free body diagram for each, breaking them up into the x and y direction with our cut and paste step. So two objects gave us 4 equations, one of which was a simple equation, and we always pointed our axes in the direction of acceleration. For problem number 2, this was intended to be kind of give you a reminder of the first block, because we said it started from rest. You could find the acceleration, right? You plugged into this equation and found the acceleration is just a number. And when we did kinematics, we used acceleration without giving thought to what caused it. Now that we're doing Newton's second law and analyzing forces, we're understanding where that acceleration comes from. So we're just trying to draw that connection by having you solve for the acceleration and then plugging it into a kinematics equation to find what the final velocity is. Because we can use that if it's a constant acceleration, which this is, we can use kinematics to understand that motion. We do that by plugging into this simple kinematics equation. Hopefully we're proficient at that now. And then we did a drag one. There was some requests for going a little over drag a little bit more. So we did a terminal velocity with this unfortunate cat that's falling at terminal velocity. And it's the exact same thing, right? This is a Newton's second law problem. We do our free body diagram. We do our cut and paste step. The trick, if you want to call it a trick, is recognizing that at terminal velocity, it's a constant velocity, so there is no acceleration. So the right-hand side of both of these equations are 0. All the forces are in the x direction, so you end up with this expression that the weight force is equal to the drag force, and then I can solve for whatever it is I want. Maybe we had told you solve for the mass of the cat, and I gave you the velocity. But in this case, because you're always going to get this expression, in this case we came up with we were wanting you to solve for the terminal velocity. And those are the numbers if you actually decide to plug in the numbers. And then on the last one, again, we've got two masses. So this is a Newton's second law problem that we're going to do free body diagrams for both of those two masses. But similar to our terminal velocity equation, we're told that this is moving at a constant velocity. So the drag force, or not the drag force, the friction force pulling back on these objects is canceling out with the x component of the force being pulled forward. But you have to be careful because the coefficient of friction is acting here, but the normal force is being changed because this force is pulling up on it. So that normal force, and you can see that in the math, right? The normal force normally is just mg, but for us, the normal force is the mass of object 2. Subtract, it's smaller than that because this force that's being applied here is lifting up on the block and it's decreasing that normal force. So we just follow the math. We do the same process. We do our two free body diagrams. We align our axes in any direction this way because we don't have acceleration, but we decide to make a good live choice and align it with the direction most of our forces are pointing. And then we do our cut and paste step with the freedom of the right-hand side being 0 for all of them because the object is not accelerating. It's at a constant velocity. We end up with 4 equations and 4 unknowns, which is terrible, but a little bit of algebra, and we're able to come up with our solution for what the force is that's being applied to the block in order to meet these conditions. So I hope you found that video helpful as you continue to study and prepare for WPR number 1, and I will talk to you soon. Bye.